Hi guys, let's do the fire hose question from our packet. So we are on page 3 of the packet. This is question number 4 that says a fire hose sends 20 kilograms of water each second at 60 meters per second against the wall of a burning building. Assume that the water striking the wall does not bounce back from the wall. What is the average force exerted on the wall by the water? Okay, so here we are starting with just the information given. We have the mass of the water, 20 kilograms. The V initial, which is the velocity the water is shot at the flames with. So VI is 60 meters per second. And then because I made that positive, I'm going to say that to the right is positive and up is positive. So again, just like in kinematics and forces, we need to set our positive direction. So towards the house is positive, away from the house will be negative. VF is 0 since the water hits the side of the house and does not bounce back. Okay, so VF is 0, and the question says, what is the force on the wall by the water? So using impulse momentum theorem, which is F delta T equals M delta V, I'm writing down the equation I'm going to use. And again, I've been reiterating this in class that you guys should write down the equation whenever you use it. Okay, it's going to help you to remember it and understand it a little better. Then second step is to solve in variables. So divide by delta T on both sides. And I get F equals M delta V over delta T. I know that delta V is V final minus V initial. So I have F equals M times the quantity VF minus VI over delta T. Okay, now I can plug in numbers. We have a mass of 20 kilograms, a V final of 0 meters per second, a V initial of 60 meters per second, and a delta T of 1 second. And so for some of you, it was not very clear where the delta T came from, but it was from the given information where it says a fire hose sends 20 kilograms of water each second. So we're looking at the frame of reference of 1 second. So I have 20 kilograms times negative 60 meters per second. So that is negative 1,200 newtons. So since our answer is negative, this tells me that the force that I'm talking about is pointing to the left. So that would be the force on the water by the wall. And I believe this question says, what is the average force on the wall by the water? Okay, so this is the force on the object by the wall, and the question asks for the force on the wall by the object, so we would just change the sign and say that our answer is positive 1,200 newtons because it would be pointing to the right. This is the force on the wall by the water. Okay, so this was part A. Part B is conceptual. Part B says, if instead the water bounced back somewhat from the wall, so it doesn't tell you how much, but it just tells you that it bounces back, would the water exert more or less force on the wall, and why? And intuitively, a lot of you said more force. So this would be the same thing as if a large boulder was rolling at you. Would it take more force for you to stop the boulder, or for you to stop the boulder and then roll it back to where it came from with some velocity? And of course, all of you would say, well, it would take more force to not just stop the boulder, but to also change its direction. But there's an algebraic reason why. So let's say, for instance, the water did not stop at the wall, and the water actually bounced off the wall with the same velocity in the opposite direction from which it started. So let's say that VI was still 60 meters per second, but now VF was negative 60 meters per second. Let's see what happens to our momentum and therefore our impulse and force. So if we have F equals M VF minus VI over delta T, and we still have 20 kilograms of water. This time VF is negative 60 meters per second minus our V initial of positive 60 meters per second, all divided by delta T, which is still 1 second. You can see that this simplifies to be 20 kilograms. A negative 60 minus 60 is going to be a negative 120 meters per second divided by 1 second. So the quantity that we get for our force, 20 times negative 120, negative 2400 newtons. But again, that would be the force on the object, so on the water by the wall. And if we're looking at the force on the wall, we know that this would be positive. So force on the wall would be 2400 newtons. So we actually doubled the force if the water bounces off with some velocity equal to the initial velocity. Okay, so the reasoning behind this, the algebraic explanation, would be that delta V increased, therefore the force increased.